Yeah, there was a discussion on the Google groups for the Keysight Agilent HP test equipment forum on offset, well, not necessarily offset shorts, but calibration standards, and whether placing a short circuit, ideal short circuit at the end of a coaxial line, whether that has inductance. Um, I was under the impression that it did. When you have an open, you have fringing capacitance at the end of the line, and you can correct for that with a polynomial error model to calculate the frequency dependent capacitance. But the inductance in the correction coefficients for the cal standards, there's typically a delay. That's the time delay between the reference plane and the actual short, because it's an offset short. And but there's no inductance there. The model provides for a polynomial inductance, but the coefficients are all zeros. So there's a discussion ongoing on whether there actually is an inductance there or not. I was under the impression there was, but someone had mentioned that since the shorting plane is solid, you can't have a magnetic field creep around through the backside, of course, and come back around. It can't form a loop. Therefore, we'll have no inductance. And since it's a TEM wave, propagating down the line and hitting this ideal plane, it's going to reflect right back, and there's not going to be any inductance. So what I wanted to do is kind of go over that and simulate it to prove to myself that that was the case. So I've got this piece of paper right here. I've drawn a 3.5 millimeter coaxial cable. It's got an outer diameter of 3.5 millimeters, and we need to calculate the inner diameter. So we're going to simulate this in a 3D solver and try to find out what the reflection coefficient is at the end of the line. So if you look at Brian Waddell's Transmission Line Handbook, this thing right here on page 47, you can get the formula for the characteristic impedance of a coaxial line. It's just the impedance of free space. Accounts for the dielectric medium inside the line. Then big D is the outer diameter and little d is the inner diameter, and it's a natural log, of course. So you can solve for D, little d, and then plugging in, I use 3.5 millimeters since that's a standard connector. So use 3.5 millimeters, 50 ohms for Z naught, 377 ohms is close enough for the impedance of free space. You end up with 1.521 millimeters for this inner diameter. And then, well, how high do we want to analyze this line? So let's find the where the TM mode is approximately ends. Again, this formula a couple pages later, we can calculate that using the outer and inner diameters. It's when it comes out to about 7.89 millimeters for a wavelength. When you get a half wavelength around here, around the perimeter on the average on the inside. And the cutoff frequency for that is going to be 38 gigahertz. So 3.5 millimeter lines can typically be used to 35 gigahertz. So I'm going to go ahead and use that to analyze it. We'll plug these into our simulator and set the maximum frequency to 35 gigahertz. So this is a view, of course, of the end of the line. Here's a view of the side of the line. I want to make this thing about 10 millimeters long because we're going to have a wave port right here, and we're going to have a discontinuity right here. You want to be about 3 times the diameter. That comes out to approximately 10.5 millimeters. But any discontinuity you want to have your wave port away from so these modes can die out, have sufficient time to die out before you try to do a reference impedance right here for your reference plane. So setting a length of 10 millimeters should be fine. So I've drawn. You can see a TEM propagation. You're going to have your E field, in the plane right here. H field is coming out of the plane, then going back in, circling around the inner conductor. We're going to have surface currents, on the inner conductor, and the return current is going to be on the outer conductor. But the question is there an inductance right here? We're going to have current creeping up this shorting plane right here, but do we have an inductance? If you model that short circuit, as a small inductor, that's equivalent to a short transmission line, much less than 90 degrees is going to be equivalent to an inductor, which means there's going to be a time delay. So the question is, there may not be any inductance used in that polynomial model, but if there is a time delay, maybe it's embedded in the distance between the reference plane. You have an offset short, so you've got this distance which your cal coefficient has to account for, but is the delay that's right here embedded into that, or is this going to be zero delay? If you take the length right here, which is going to be about 1 millimeter between the surfaces of the conductors, you look at the time delay, assuming speed of light propagation, that's going to be about 3.3 picoseconds to creep up this wall and get to the outer conductor. Our maximum frequency of 35 gigahertz, that would be approximately 42 degrees. So we simulate this, and what I'm going to do is set this model up, then shift the reference plane 10 millimeters all the way to here. So we should get an ideal short circuit on the Smith chart, with a phase of 180 degrees. But if there is a delay in there, you're going to see it creep up, around the outer edge of the Smith chart, creep up there by 42 degrees at 32 gigahertz, or some number close to that, maybe less. But we're going to see if there's a phase creep or whether it's going to be an ideal short, and we'll have to run the 3D simulator to find that out. So I've got Microwave Office here. I've already got this project set up. I erased the simulation results so we can restart it again. But I'm not gonna walk through the whole project, how it was set up, but I'll just show what's in it. I've set an arbitrary 3D EM structure here, ready to be simulated by Analyst. I open that up in the 3D editor. You'll see it is right here. So what I've done, I've defined a outer conductor, which I've essentially just drawn a brick of material. It's about 6 by 6 millimeters. I've made it 11 millimeters deep. And we're going to make the coaxial depth 10 millimeters. So we'll have about a 1 millimeter. Not that it makes a difference. It could be infinitely thin, but we'll leave a little bit of space down there. So I've got, and then I took a dielectric and inserted that into it. And then also a center conductor. So if you look at the whole thing, you've got this center conductor, which goes down into that dielectric. Everything's 10 millimeters down, and it's everything's made out of perfect electrical conductor. And then I've added a wave port to this face right here. There's several ways of drawing this thing. I mean, you could use a pipe. I ended up using just a cylinder. You could put a pipe and insert just the dielectric into there. And I think this version of Microwave Office, the dielectric will override the conductor, but you do have to have a dielectric on the surface, because when you define your wave port, it's going to want to see a dielectric, and of course that's going to be air in this case, but it still has to be defined. So now, and I've gone ahead and parameterized. I've got D right here for the little diameter of the inner conductor, so we can change that if needed, but everything else is just hard set, for the dimensions. Now I can close this out. And you can see here it is back in the 2D editor. I've got my wave port right here. So I'll go ahead and bring up. I've got the input impedance, and what I did, let me go back actually here and show this. I forgot to show this when I had the wave port up. But if I take and look at this wave port, I've set this reference plane shift to 10 millimeters, so it's going to go from the reference plane and then go back all the way to the shorting plane. So if it properly computes the propagation constant, it can de-embed that out and move it so we get the results right at the reference plane, right? Excuse me, at the shorting plane. So let me close that out again. So we can look at the input impedance de-embedded back to the shorting plane. And then also it's a good idea to look at the port impedance, because at first it's got to do the port solve on its face. We want to make sure that's pretty close to 50 ohms, or else the propagation constant could be off, and we're not going to get an ideal short readout once we do de-embed through there if the constants are wrong. So I'm going to go ahead and let this thing run. Actually, I'm going to cancel it real quick because I want to show one thing. I changed some of the options in here. We go to the Analyst options. We're going to want to take a look at the field output frequencies. We need to change that to the adaptive mesh. Otherwise, it wouldn't give us any field output frequencies. And then frequency modifier. I've set this up to solve from 1 to 35 gigahertz. We want to set this to high, so it's going to do the mesh adaptation at 35 gigahertz instead of mid-band, which is going to be around 16.5 gigahertz. And minimum mesh convergence is, I've set the tolerance. This is normally 0.02, which is 2% S parameter tolerance. Change in S parameters from convergence to convergence. I've tweaked it down to 1%, so it's a little more accurate. But set the minimum mesh convergences, so once it hits that 0.01, it's going to continue on until it gets 3 in a row that are below that. So that will take care of any oscillations that could occur if it creeps up above that 1% and goes back down. That will give a good solid result. And then that was for the ports, the port phase we're going to solve for the wave port. And then I have the same settings for the full solve when it's going to solve inside the air in here. It's also 1% and 3 mesh convergences, and that's about it. Go and hit OK, then I'll go ahead and hit solve. And now you can see, so it's starting off, it's doing the ports right now, and it's going to get 3 port solves where we have less than a 1% error in a row. This is actually going to take a little bit of time. You can see it's starting to mesh right now, and the mesh is going to refine and get finer and finer. You can see it's doing a very fine. If I zoom in here, going to start refining the mesh on the port face, and once it gets that port solution, it's going to start refining the mesh on the inside, down inside of there, but it's got to get the port solution first. So, and you'll start seeing the now we're starting to get the result right here. You can see it's about, well, what, it was 175 degrees. It's not a perfect 180 degrees. But as the mesh refines, it's going to start creeping back down again. So now we've met the, we've gone below the target delta S of 1%. And now it's got to get 3 more of those in a row. And you can see for the third mesh iteration, it actually crept back up. So it's going to have to solve for a little bit. Normally you'd never do this for a typical design. You wouldn't do the mesh adaptation, a good mesh adaptation until the end, to make sure your results are I guess precise or accurate. Typically, what you want to do is keep refining your mesh until you get no changes in the S parameters, and then maybe back that mesh refinement off to pick up some speed. So this has a little bit of a ways to go still. But you can see it's refining the mesh now down inside the conductor, and it already has the port solution. For some reason, it's not putting the port impedance up here. I think it will when it's done. So we're on 6 adaptions now, and it's almost below that 1%. But you look at the input impedance now, it's dead nuts on about 180 degrees, 0.7 degrees off. So now we're at 7, and we've converged below the 1% error. And as you can see, the mesh refining in real time in the mesh plot here. That's good. Now we're on an 8th now, and we're pretty stable, it looks like. And we've actually gone 0.2 degrees, closer to an ideal short circuit. We crept up a little bit, but we're still below. So this, I think, is going to be the last one, since we've got 1, 2, and 3. And it's doing this at 35 gigahertz, and then once it's got that, it'll go back and solve the remaining frequencies. And I've also defined. We can reduce this some. I've gone in here and under annotations I've added some field cut plots and current plots. Take a look at that once this is done, since it's going to be hard to try to fit all this on the screen at once. And that's a way overly meshed down inside of here. But again, we're trying to pick up very fine phase resolution in here and make sure we get a good result. A sufficient answer probably would have been right back here, you know, at the second mesh iteration. There we go, and that took about 6.5 minutes to do. Now you can see we're extremely close on the impedance. I think, what is that, 35 milliohms off from an ideal 50 ohms, and the phase right here is again dead nuts on it. We look at that. There's just a very slight amount of error. You can see it's going below. You know, it's going down to like negative 179 point something down here. So this is going to be error in the simulation. Not, you know, obviously it's impossible for it to go negative in phase, you know, because we have a short right there, but that's just, you know, meshing errors and other sorts of things that are going to creep in. But, you know, looking back here, we are well below this 42 degrees that we, you know, that we could have gotten if there were an inductance or a time delay in here. So I think it's sufficient to say that, you know, there is a pure TEM reflecting off this boundary right here, since there are no gaps in the boundary. And if you think about it, you know, an infinite ground plane has zero inductance, you know, and it requires it to be infinity because the magnetic field can't loop around and encompass that conductor at infinity. So if you look at a plane wave reflecting off a, you know, you've got a wall right here, a plane wave comes in, hits that, reflects back off. There's no inherent time delay in that reflection, again, if the plane is infinite. So I think the same can be said of this short circuit at the end of the TEM conductor, in that the only time delay you have to have now is to resolve the difference between, you know, your reference plane right here and the end of the short circuit. So now let's take and close these, and let's bring up some of these field plots. So let me take and make that a little bit smaller, and let's go ahead and window, new window. So that's going to bring up window number 2, which I've defined as a surface current. You can see I've got view number 2 right here. So I go ahead and add a cut plane to that. Go right here. There we go. Get about in the middle of the thing. So now you can make this bigger. Now you can go and see the currents on the surfaces. We animate that. You can see you've got the currents, going down in one direction. Their turn currents go in the opposite direction. And there's the current on the wall right here. That current is not contributing to, does not have an inductance because it can't store any energy, in a field, because the field can't get through that ideal shorting disk right there. Now let's close that and bring up, got to bring up another window number 3 right here. So in window number 3, which is right here, I am looking at the Y-directed electric field. And see, I've got that cut plane there, so I'm looking at the Y-directed electric field on that cut plane. And you can see it's coming up, obviously, and going down out of phase because it's 180 degrees length between here and here. It's at 35 gigahertz. And of course, once the blue that you see right here is the perfect conductor, so it's going to go near 0 right here. But you can see it's peaking out at 1.4 times 10 to the 3 volts per meter. I bring up the next plot, new window. So this is going to be the Z-directed, the field, electric field in the Z direction. And you can see there's a lot of kind of some weirdness going on here. Again, there shouldn't be any Z-directed electric field at least in the TEM section of the line. If there's a discontinuity at the shorting plane, you would have to see a Z-directed electric field, and we're not seeing anything like that. There may be a little bit of a 1 here, but is that due to the shorting plane, or is that due to numerical error? Because we're seeing it right here also 180 degrees later. If you look at this is 32 volts per meter. If you take 1.4, say 1400, and divide that by 32, take 20 log of that, that is going to be 33 dB. So that is likely numerical error right there. And I think again it's safe to say that it's a perfect reflection off there. There is no inductance or no time delay down at the end of that short